Alrighty, let's go ahead and get started now that everybody's here. So what are we doing today? So we're gonna continue on from last time. Basically, we talked about how to do the chain rule. We talked about ways to break it down to feel easier, and then by the end, we were slowly getting into the fluency of being able to take the chain rule and just do it without all the extra steps. Today, what we're going to do is we're going to continue on that road and we're going to work on uh, more complicated ones. And so I want to get through as many of these as possible while still giving you time to practice. If we go through the first couple of these and you're like, oh yeah, this is simple, this is easy, then go into the Math Excel and do that. But if you're still feeling sort of edgy about this, even after the first couple, stick with me. I'm going to be going through as many as possible. Okay. So let's start with this one. I want to start pretty simple. So the first thing I want you to do whenever you encounter a square root or a cube root or fourth root or whatever kind of root, rewrite it as an exponent because it'll make your life so much easier. A square root, remember the index here is a 2, so this is to the 1 over 2, right? Now, when we want to take the derivative of something more complicated like this, remember we're taking the derivative of the outside times the derivative of the inside. So you can start off by pretending that this piece in here isn't anything. Just ignore what's inside the parentheses and pretend like you're going to take the derivative normally. So we're going to do bring down the 1/2. And then we're going to take this exponent, lower it by 1. 1/2 down 1 is negative 1/2, right? And then we're going to multiply it by the derivative of the inside. Well, what's the derivative of the inside? Well, let's take it piece by piece. Don't try and do it all at once. Remember, especially when it's a polynomial like this, you can just take the derivative of each individual piece. The derivative of 8, that's 0. Okay, move on. The derivative of negative 3x, well, that's just negative 3. And that's that whole thing. So now, I mean, you're done basically. But if you want to make it look nicer, you can rewrite it. I'm going to take the negative 3, bring it up front, and put it in the numerator of that fraction. And then you can either, in my opinion, leave it like this, or sometimes they'll want you to not have any negative exponents. On the AP exam, it's not going to matter. If you give them this, if you wrote that down on the free response, and that was equivalent to the correct answer, you get full points. But like on Math Excel, if they give you specific directions, write it with no negative exponents or write it as a radical expression, then you could negative 1/2 means bring it down to the bottom and put the square root back on. So you could, if you wanted to, write it like that. But like anything in between here, as long as it's the exact same, you're okay. You're definitely fine by me, and you're definitely fine by the AP test. I'm just, the reason I'm throwing it out there that hey, these are different options is because like when you go to college and you take a class like this, maybe the professor has a specific way that they want to see it, but usually they won't. And that's because they're not the ones grading it. They've hired someone else to grade your work for you. And so they're just forced to sit there and slog through for like pennies an hour. A friend of mine was doing that for a while, and she did not enjoy it. Being a grader is incredibly thankless. Okay, so going through here, take a look at what we have. We basically have two different pieces, right? we've got the 9 over 4 pi cosine 4t plus 9 over 8 pi sine 8t. So here's the thing, this plus sign in the middle, that's great. That's excellent. That means that you can take this problem and split it up into two different pieces, break it down separately. Don't try and do it all at once. You are going to start leaking brain fluid out your ears. Do this part first. So look, when we take the derivative of cosine, we get negative sine, right? And that should be a 4. Stylus keeps doing a thing. Every time the 4. Just to connect all that together. So we took the derivative of the outside. Now we have to multiply it by the derivative of the inside. And I'll tell you, especially when it's this simple, you can see the pattern, right? We're multiplying by the derivative of the inside, so it's like just bringing out a 4, right? That's this part. And then we're going to do the same thing with this part. The derivative of sine is cosine. And, leave the inside the same. And now multiply it by what the derivative of inside the parentheses is, and that's just 8. And then again, I'm not saying that you have to, but you can simplify this, right? Negative 9 over pi sine of 4t. Bringing that 4 up to the front and simplifying. And then bring the 8 up front, 9 over pi cosine 8t. And that's it, right? Again, don't try to do too much. Don't overthink these. Don't turn this into a problem that is going to cause anxiety. Break it up. Do one piece, then do the other piece. And again, if you left it here at this first line, you're fine. If you wanted to simplify it, neaten it up, that's great. You're not going to get any extra points for that. And make sure you do it right. Because if you do the simplification wrong, they won't give you the full points, even though this part was correct. So I'm not saying you have to leave it like that one, but if this one's right, leave it. Because if you do extra work and it's wrong, suddenly you're wrong when you shouldn't be wrong. It's points that you're giving away. So leave it in this gross, ugly form so that you don't have to do any extra work. Sounds like a win-win to me. All right, take a look at this one. So again, we've got this outer function, this to the negative first power. So we're going to have to deal with that, and then we'll take the derivative of all the stuff on the inside. So once again, we're going to use our power rule, bring it down. All I did is I took the derivative of the outside part. I didn't change anything in here. Now I'm going to multiply by the derivative of what's inside. Now, once again, like I said, I don't memorize these because and it's like it's hard to memorize, I think, sometimes. It's difficult. And so I personally have trouble. I'm not going to say that it's the easiest thing in the world. But like, okay, so we want to find the derivative of cotangent. What's the derivative of cotangent? That's negative cosecant squared, right? And then minus, what's the derivative of cosecant? Negative cosecant cotangent. So negative, negative, that's a plus now. And again, are you going to do extra work here? Don't. You shouldn't. There's no reason to. You probably could simplify this, but why? Why do it? There's no reason. Leave it like this. You are done now. The AP exam is going to be like, no, you can leave it like this. Here's all your points. So again, you're taking the derivative of the outside part, and you're multiplying it by the derivative of the inside part. Again, don't overthink this. Now, I'll tell you, I really dislike the note, even though it's like standard notation, having the exponent be here in the middle. It makes life harder for everybody. So it does help, especially for chain rule, while you're still learning, if you rewrite it in a less odd notation. See, because now here's the thing: we've got chain rule, we've got product rule. So let's take this one step at a time. Because you know that you're going to have to do product rule, and doing the derivative of the polynomials is pretty easy. The part that's going to be a pain in the butt is this one, right? The sine x to the fifth. So let's take a second and let's just take the derivative of sine x to the fifth and cosine x to the negative fourth. All right, and then we'll be able to work our product rule a lot easier once we have all of that. So the derivative, I'm going to put it up here just out of the way so that we can see it. The derivative of this, again, we're going to take the derivative of the outside times the derivative of the inside. So bring down the 5. And then multiply it by the derivative of the inside. Well, what's the derivative of sine times cosine? So that's the derivative of that part. Let's do the derivative of this buddy right here. And we look, okay, we're going to take the derivative of the outside, so bring down the negative 4. Cosine x, and then we bring it down 1. Negative 4 down 1, now it's negative 5, right? Times the derivative of the inside, negative sine x. All right, so we've done all of the things now. I can actually simplify this one a little bit to make it look neater. The negative and the negative cancel out, and we're left with 4 sine x cosine to the negative fifth x. Same thing here, 5 sine to the fourth x cosine. But so now that we've done this, this is going to be a lot easier to do now because we've got all the hard work done. So look, left d right plus right d left, right? So left d right, left d right. X squared times 5 sine to the fourth x cosine x plus right d left 2x sine to the fifth x. That's this one. Plus left d right plus right d left. So we've got x times this here, 4 sine x cosine to the negative fifth x, plus right d left. Derivative of x is just 1, so And now we can leave it like this, or I'm just gonna, neaten it up a little bit. This part here, let's rewrite it as 5x squared. And then we've got the sine to the fourth cosine plus 2x sine to the fifth x. And then let's sort of simplify this, make it look a little bit neater. 4x sine x cosine to the negative fifth x. And I put sine first and cosine second. It really doesn't actually matter. Plus cosine to the negative fourth x. And here is our dy dx. Now, once again, make your life simple by taking the weird parts and just doing them off to the side separately, so you don't have to think as hard. This, once we wrote it out, it was so much more simple because we put all the effort up here. Take the time to do the difficult stuff, put it off to the side so you can breeze through the problem. Okay, let's keep on going. Same idea, same exact problem, just now with a bunch of polynomials instead of a bunch of trig stuff. So once again, left d right plus right d left. Well, let's get our d left and our d right. So when you do this one, you bring it down, and then you multiply it by whatever's 4 goes down to 3, right? And then multiply it by the derivative of the inside. Derivative of 5x plus 3 is just 5. And our d right, our right-hand side, once again, bring it down. Don't change the inside here. Make that be 1 less than it was before. Was -2, down to -3. Times the derivative of the inside. Derivative of 4x plus 5 is just 4, right? So now that we've done this, we've got our left d right plus right d left. So let's write it all down here. Things not picking up on the screen. Our y prime is left d right left d right. So we're gonna maybe simplify this out. -2 and 4 is -8. They're on the outside. Times 4x plus 5 raised to the -3rd. And we'll clean this up in a little bit. Plus right d left. 4x plus 5 to the -2nd times d left. 4. And again, let's maybe neaten that up. That's a 4, that's a 5, so that's 20. 5x plus 3 cubed. And then again, you can leave it here. You can just, you're done now, right? Nobody's gonna force you to continue, but you could neaten this up. You could make this look nicer if you wanted to. Bring this -8 out front. And then this 4x plus 5 to the -3rd, you could bring it down into the denominator like that. And then you could do the same thing here. You could bring that down into the denominator if you wanted to. Again, when it comes to the AP test, don't do too much. I wouldn't, honestly. This is this is more than good enough, this line, that's fine. You're done. But like, you know, if you need to do more with it, sometimes it does help to clean it up so you actually have less work to do later on. Okay, let's keep going. Again, a lot of this stuff you can just breeze right through. Like here, don't be intimidated by how gnarly this is. Remember, we're going to take the derivative of the outside, multiply by the derivative of the inside. So let's start off. We've got our function, and we want to find our derivative. So bring down the 2, cosine, and again, this whole part you don't change anything. Then we're going to multiply it by the derivative of the inside. Well, that's more, right? There's more to that. So let's maybe do the quotient rule. Low d high minus high d low over low squared. So we've got, here's our low, here's our high. And what's our d low? Is derivative of 1 is 0 minus the derivative of sine is cosine. So d low is negative cosine. Our high is cosine, so our d high, negative sine. So we got low d high minus high d low over low squared. Low d high times negative sine x, we'll put a negative out front, minus high d low, high times d low, over low squared. So yeah, I mean, like, stop here. Why do more unless you are absolutely physically forced to? I wouldn't. There is some stuff that I noticed that you could do, like especially in this part, like if you distribute the negative sign and the sine x and the distribute the multiply this stuff here. And you've got the -1 over sine, -1 minus sine x. You could turn this into like a cube thing. This part becomes something kind of fun, actually. Negative times -1 plus sine squared plus cosine squared. Oh, does this really come out to 0? That's awesome, actually. Because look, sine squared plus cosine squared, that's the Pythagorean identity. That's 1. So you got -1 plus 1, right? Yeah. So this ends up actually being 2 times cosine times 0 over 1 minus sine of x cubed. So this actually ends up being 0, but you don't have to, unless unless you were given specific instructions. Simplify completely, or you're in a multiple choice section where they're going to give you the simplified answer. Ain't nothing to simplify. If you're in a situation where this is what you've got, leave it for the grader to handle. Why wouldn't you? All right, so one of the things that I've noticed people have a lot of trouble with is when you've got e to a thing. So first of all, let's take the derivative here. Again, it's, the derivative of the outside times the derivative of the inside. So we've got Derivative of cosine is negative sine. Times, now we're going to take the derivative of the inside. Well, the derivative of anything, e to the anything is just e, right? And now notice there's a whole thing up here. So now we're going to multiply by the derivative of what's up here. Well, our thing is theta here, right? So we're going to treat this like a power rule. Bring the 5 down. And theta's our variable, x, whatever. And then it was a 5, now it's a 4. And that's all there is. So how would I take all this and simplify it, make it look nice? Here's how I would do it. This is just me. I'm gonna first, so all this is multiplied together, so I know that it's simple to just move stuff around. These two negatives are gonna cancel out. I like the fact that this book uses a whole bunch of different variables, forces you to sort of just dissociate from variables and just be okay with any old thing. So this 20 theta to the fourth times, I like to put the exponential stuff next, times e to the negative 4 theta to the fifth times sine of e to the negative 4 theta to the fifth. A little bit more simplified. It looks a little bit better, I guess. But once again, make your grader earn their money. Don't be afraid to just leave it like this top one, because if this bottom one isn't the same, then they're going to mark it wrong and they're going to give you, they won't give you the points that you deserve. So always do the least if you can help it. Really, honestly, always do the least if you can help it, because it's going to mean that, one, you have more time for other stuff, and two, you're going to be more likely to earn points on that free response section. All right, here's the same thing. And once again, this sine squared thing here, take a second and rewrite it like this so that you see what's going on a little bit easier. And you can put it back later if you want, but it's up to you. So again, we're gonna first take the derivative of the outside. Well, what's the derivative of e? It's just e, right? So this part doesn't change. Then we're going to multiply it by what's up here. And what's up here, I want to take it apart for a second and show you what's actually up here. Be careful about what you do next, right? The outer function now is this power, right? So bring that power down. And again, leave the inside of the function alone. Don't change anything in here. Now we're going to multiply what's on the inside. The derivative of that. Derivative of sine is cosine. Don't change the inside. We have one more to do, right? We still have what's inside here. Pi t minus 3. Well, what is the derivative of pi t minus 3? What's the derivative of pi t? Pi is a number, right? 3.141592654, whatever. So this is just 3 point something t, so it's just 3 point something, and then that part's 0, so times pi. Hey. Now I'm down to the bottom, and I'm gonna just rewrite it for my own personal peace of mind. The 2 pi, we can put that out front. And then we'll put the exponential part next. And then put all the sines and cosines last. And this is, again, this is it written out all neatly, but hey, that's the answer, right? You don't have to simplify anything you don't want to simplify, especially on that free response section. Don't simplify when you don't have to. Don't make life harder when it doesn't have to be. All right, once again, start with what's on the outside and then work your way in. Derivative of cosine, negative sine. And then all the inside stuff, just rewrite it. Now we're going to multiply by the derivative of the inside. What's the derivative of sine? And again, don't change what's inside the cosine. Now, we still have stuff on the inside of that cosine that we have to take the derivative of. What's the derivative of 6t minus 7? Well, it's just 6, isn't it? And again, you don't have to do any more than that, but negative 6 sine of 6t minus 7 times cosine of 6t minus 7. And that's it. Again, don't overthink this. Once you're good at this, these take like 5 seconds to do. So now this one wants y double prime. So we're going to do this and then we're going to do it again. We're going to have product rule here, right? Left, d right, plus right, d left. Left, d right. So this is y prime. This is our first derivative. Left, d right. Right? This whole thing, take the derivative of the outside, multiply by the derivative of the inside, plus right d left. Don't overthink this. Don't overthink it. Don't make your life hard. But now here, I will tell you, it's a good idea to rewrite. Get all this recombined so that you have less work to do long term. This 7x to the 6th and this 5x to the 4th, we can turn that into 35x to the 10th, right? X to the 4th times x to the 6th, the exponents add, times this x to the 7th minus 1 to the 4th. Plus, and once again, rewrite it so it looks good. And yeah, I don't think there's any way to make that look any easier. So now we're going to take the second derivative. Let's do it again. The second verse, same as the first. Y double prime. So left d right plus right d left. Times x to the 7th minus 1 to the 4th. So bring down that 4. All right, bring down that 4. And then rewrite x to the 7th minus 1 to the 3rd times derivative of the inside. Left d right plus right d left. 7x minus 1 to the 4th times, bring that 10 down, 350 x to the 9th, plus, now we're going to do this one. Left d right plus right d left. I'm going to write it more down here. Left d right, bring down the 5, times right d left. Oh, you got to do this part here. 7x. So here's the derivative of that whole thing, plus right d left. Once again, times 4x cubed derivative, so 12x squared. And then once again, at this point, I'm done. Like, I'm not gonna, I mean, you could simplify stuff and make it look better, but why? Why would you do that? Period. Although these two actually kind of come out nice, which is weirdly pretty. But you don't have to do anything else here. I wouldn't. I'm just gonna leave it. I'm just gonna walk away from that. You shouldn't have to simplify it any further. Here, they're trying to make you do extra. Don't do extra. I mean, like, okay, you could do what we did yesterday, but you could also say, all right, well, I don't want to do that. I'm just going to put this radical x back in. Right? Radical x is x to the 1/2. So u to the 5th. So this is x to the 5/2 plus 7. And now we don't even have to use chain rule. I don't know why they would want us to use chain rule for something like this. That's dumb. That's dumb. No one is ever going to ask you to do chain rule if you don't have to. And if chain rule doesn't make sense, you have to remember chain rule is a tool. It is another tool in your toolkit. But just because we bought this really nice new hammer doesn't mean we have to use it all the time. You know, like you can, oh, this just came in the mail, but I need to put a screw in somewhere. Why would I use a hammer for a screw? You don't have to. Take the derivative. 5/2 x to the 3/2. That's our f prime. And now it said, it said at the given value, and they gave us the value of 1, right? We want to know what the derivative is at 1. Now at x equals 1, we're going to write that down. Well, f prime of 1, we're just going to put 1 in, right? 5/2 times 1 to the 3/2. Well, what's 1 to the 3/2? Isn't that just 1? 1 to any power is 1, right? Ta-da. Don't be extra. Don't do extra when you don't have to. There's no reason for you to have to do chain rule here. Sometimes you're going to have to do chain rule regardless. Like you have no choice, or the alternative is 45 minutes of garbage. Like imagine if you tried to do this one without chain rule, trying to FOIL this out 5 times and then distribute that x to the 4th in and then take the derivative of that polynomial. You could do that. It would take longer than this, but you could do that. But ain't nobody got time for that. Here, the chain rule is possible to use, inadvisable to use, more lengthy to use, more complicated to use, because you can always take this and break it down easily. If you can take something and break it down easily, break it down easily. Always try and do easy algebra before you do anything else. Because if you can do a little bit of algebra and make your life simpler, It's going to make your life simpler. You know, that's the thing. It's going to make your life simpler. All right. I really, really, really wanted to get to this one, and I'm really excited that we're just sort of getting to it. Because this problem here looks exactly like something I would see on the AP exam. Here they're giving you a chart and they're giving you just general values, and you've got to come up with something that you just get. So they're saying they want to know the derivatives of each of these situations at the place that they want. And there's a bunch of them. I'll do a couple of them. So you've got, like here, 2 to the f of x. Well, take the derivative of that, and that's just 2 times f prime, right? And then they want it at 2. Well, so that's 2 times f prime at 2. Well, where's f prime at 2? That one, right? So this is 2 times 1/5, which is 2/5. And that's the answer to that one. A lot of these are very simple. This is like 1 and 2, very simple. 3, they want you to use the product rule, right? Left d right plus right d left. So for C, left d right plus right d left. At 3, right? So we've got f of x at 3 is 3. G prime of x at 3 is 3. G of x at 3 is -5. F prime of x at 3 is, I think that's a pi. Yeah, that's a pi. It's in the way. A little circle times pi. And then just simplify it. 9 minus 5 pi. Right? It's just take the derivative symbolically, then plug in the numbers and get your answer. I want to do one more. Let's do H. Let's do H. I'm going to make some room for H because H looks complicated. So we got the square root. So I'm going to begin the process by rewriting this in a less ignorant manner. Because it looks super duper ignorant right now. And I want to make it so it's friendly for taking the derivative. All these radicals and putting the 2's in weird places, that ain't go. So I'm going to take the derivative. Remember, first take the derivative of the outside. And I almost put an equal sign there. That would be a linkage error because I'm going from the function to the derivative. So what happens? I'm going to do the outside. And then I'm going to do the inside. So once again, remember, you're going to take the derivative of each of these, and the derivative of f of x squared, you're going to take the derivative, bring down the 2, and then take the derivative on the inside, right? 2 f of x times the derivative on the inside, right? The derivative on the inside here, which is f prime. And if you notice, this one's basically the same thing, right? 2 times g of x, and then bring the inside, take the derivative of that one. So now I'm just going to plug in numbers, right? F of x, we're working at 2. We got 1/2. F of x at 2 is 5, so we got 5 squared. g of x at 2 is 2. So 2 squared to the negative 1/2. And then 2 times f of x, so 2 times 5 times f prime is 1/5 plus 2 times g of x, so that's 2 times and negative 5, right? 2, 2, negative 5. So am I going to stop here? Yeah. Because do I need to go any further? I don't. Why would I want to? Why would I do any further? Like literally, you put it like this, your grader has to sit there and crunch those numbers. This is the final answer that you can give, and then you will get all the points. This is the type of problem I was talking about. And I love the fact that you can just stop here. Once you've plugged everything in, you can just stop and say, I'm done, and then move on. Do that. Like really do that. Don't let the grader feelings be hurt because they have to work for their money now. All right, now once again, I want to talk about find the tangent too, right? We've done this problem 1,000 million billion times now. What's our m? What's our x1? What's our y1, right? Well, x1 is -2. Y1 is going to be whatever you get when you plug in -2, and m is going to be whatever you get when you take the derivative and then plug in -2. So let's get our y, because I want to do that first. So at 2, we're going to get our y value. -2, my bad. So -2 plus 1, -2 plus 3 squared. We're going to get -1 over 1, which is -1 squared, which is 1. So our y value is 1. We found it. Now let's take the derivative. Once again, we're going to take the derivative. We're going to bring down the 2, and then we're going to do our quotient rule. Low d high minus high d low over low squared. D high is 1, so I'm just going to keep on going. High d low, well, that's just 1 again, over low squared. And then I'm just going to, like, plug in -2 again, right? Or you could simplify this. If you notice the x's cancel out, you're left with, once you do all your work here, 4 over x plus 3, the quantity squared. That helps make it easier, right? Less work. And now we're going to say again, I want to know what the slope is at -2. So let me plug in -2. I get 4 over -2 plus 3 squared. Well, that's just 4 over 1 squared, which is 4. Now my slope is 4. Hey, x1, y1, m, y minus y1 equals m times x minus x1. Right? Easy. Find your x1 and your y1, make sure you have all that. Take the derivative, plug in x1, and then just make your tangent line equation. Simple. I think we've got like 2 more. Once again, hey, find the tangent line to the curve. Here. So we got I want my y, right? Because I got my m, that's 7. Oh, sorry. My x1, that's 7. My y1, I'm going to find. My slope at 7, I'm going to find. So let's do that now. So I got 14 times 7 pi times the tangent of 7 pi over 28. Well, that 7 pi over 28 simplifies to pi over 4. What's the tangent of pi over 4? What's the tangent of 45 degrees? Isn't that where sine and cosine are the same? So the tangent of pi over 4 is 1. So y is 14. And now all I have to do is take the derivative and find my slope at 7, right? So let's take the derivative. We've got y prime equals 14 times, what's the derivative of tangent? Isn't that secant squared? Yeah, it's secant squared. Of that garbage in the middle. Times the derivative on the outside. That's just an x, so it goes away and we're left with pi over 28, right? So the 14 over 28, that's 1/2. So pi over 2 secant squared of, and then I can plug in 7. And I'm going to see that that's pi over 4 for secant, right? And so I'm going to go through. I need to like figure out, okay, well, secant, we're talking about 1 over cosine, right? Cosine of pi over 4 is radical 2 over 2. So secant is the opposite of that, right? Or the reciprocal of that, right? And now we want secant squared, so we're going to square that. Pi over 2 times 2 squared over radical 2 squared. Pi over 2 times 4 over 2. That's 4 pi over 4, which is pi. So there's my slope. It's pi. So once again, my tangent line, y minus y1, equals m times x minus x1. There's my tangent line. I did it. And it's the exact same thing that we've been doing every single time, right? It's the exact same process, the exact same thing every time. Make sure you have your x1, make sure you have your y1. If you don't have it, plug it in to the original and get out your y1. Then take the derivative, plug in x1 so that you can get out your slope, and then make your slope point slope formula, and then you're done. Hooray! Don't work too hard on this. Part B is a really interesting thing that kind of we need to look at it like a picture of it. See if I can just get straight to it. See if it'll let me. Let's go straight to Desmos. Okay, I guess I will just do. No, I'm just gonna do just straight up Desmos. I'm not gonna try and search for something special. All right, so let me pull this up here. Let me pull this up for you all as well, just so you can see what I'm doing. Desmos. Okay, so we want to know about, so our question was, what's the slope of the curve with the smallest value between -14 and 14? Give reasons for your answer. Well, let's look. Notice secant at its very lowest ever. Y'all can see at all the multiples of pi is at 1. It never, I can zoom out a little bit. That's the way secant looks. Secant squared looks. But this bottom part is always and forever at 1. It would be the same thing if we were doing with cosecant, right? Again, the same thing. The lowest point here is at 1. And so what ends up happening with secant and cosecant is like there's a minimum value for these, for the squared version, not the original. Welcome back, by the way. So, but the point is, you go through, whether it's secant or cosecant squared, got this minimum value at 1. And so a problem like this, where it's asking about what's the slope of the curve with the smallest value, just look at it, right? Especially we're talking about secant squared. You've got other options technically, I guess. You could, and we'll talk about this a lot more and practice it a lot more later, but you could, when you see smallest value, you should be thinking a minimum, and we'll talk about how to do that with calculus later. But like for now, you can just look at this picture and say, hey, well, the minimum's always at 1 here. All right, let's get back to our problem. So like for part B, the answer is just 1, right? Because the secant squared, that was our derivative. That's where we find the slope. And so the smallest value here is going to be when this is at 1. So like you go through and secant squared can only be as low as 1. And so we end up with the smallest it could possibly be is pi over 2. Let me show you algebraically what I'm talking about. I'm saying a lot of words, but I'm not writing things down. That can be a pain in the butt. Let me scooch this up. Scooch that out the way. So our slope function is this. And what we were just showing on Desmos is that this part, because we want smallest. The lowest this ever gets is 1. This only ever gets as far down, like when we were watching the thing and it was doing the little wibble wobble thing with the weird fingers coming down from the sky. We saw that the bottom of every curve was at 1. So that's the lowest this can ever get. And so the slope, the lowest the slope can ever get is this being 1 times whatever this is. So 1 times pi over 2, which is just pi over 2. So the answer to part B is this thingy right here. Okay, last thing. And I wanted to talk about how they give you a picture, but like you don't need no picture. They give you everything you need right here. And so they want to know on what day is the temperature increasing the fastest. So what they're really asking is on what day is the speed of the temperature fastest. Increasing the fastest, what they're asking about is acceleration. So what you need to do in order to get the answer to this correct and answer it correctly is you need to find the second derivative, right? And how many degrees per day is the temperature increasing when it's increasing the fastest? So you're going to find your answer here. What is your y double prime? When is that increasing the fastest? Set that equal to 0 and solve for x. And then you'll get your x value. And then what you can do is you can plug that into your original y prime. How many degrees per day? This is the key. Degrees per day, right? Right. This is the velocity. So you're going to come in and you're going to plug that into y prime. Now, we got about 17 minutes left of class. I'm going to do this, but I think at this point everyone should be working on the Math Excel. So I'm going to do this. It's kind of a slog, but we're going to do it. So we've got our y, so let's find our y prime. (36) times the cosine of all that stuff in there. Plus 27, the derivative of that's just 0, so that goes away. But then we got to do times what's on the inside here. And the derivative of this, you can distribute this 2 pi over 365, and then it's just going to be times x. So the derivative of that's just going to be 2 pi over 365. Because it'll be 2 pi over 365x minus 200 pi over 360, but it doesn't matter. That's a number. The derivative of that is 0, right? So now to make our lives simpler, I'm going to rewrite this. 36 times 2 is 72. So I mean, each time we take the derivative, we're gonna change the trig function, but basically it's gonna kick out another 2 pi over 365. So don't feel like you have to think really hard about it. Prime. And by the way, save this function because that's what we're gonna plug. Once we find x, that's what we're gonna plug that into, right? So y double prime. Once again, take the derivative of the cosine as negative sine. Sine of this thing, 2 pi over 365 times x minus 100. And then we kick out that extra factor of, whoa, what happened here? Oh my goodness. Okay. My apologies. Times 2 pi over 365. Okay, so like I'm gonna go through and I'm gonna combine stuff. Negative 144 over 365 squared. I don't want to figure out what that is. I'll deal with that later. Sine of this. Actually, we're not going to have to. Remember, we're taking that, setting it equal to 0. This whole thing, when we try and multiply that over to the other side, is going to go away, right? So we only care about where the sine of this hideous garbage is equal to 0, right? And so where does sine equal 0? Where is the y value on the unit circle 0? It's at 0, and it's at pi, right? So we have two different answer possibilities. So we're going to have to check both, it looks like. And it may just be that we don't really care about the other one because it might just be it might be beyond the scope of our year because they only care about over like the year. It should be nice and periodic and happen at the same time every year. So what we have is this argument, 2 pi over 365 either equals 0 or equals pi. So, okay, so this one, we end up, we multiply the reciprocal over to the other side, and that cancels out with the 0, and so we're left with x equals 100. A 100 days in, that's somewhere in here, right? Maybe a little bit into April. And then here, with this pi over here, multiplied by 365 divided by 2 pi. $365 divided by 2. So the other one is 282.5, which should be something like here. Well, but this is going downward. We don't want any decreasing. We want it to be increasing. We want that one. So this one is bad. We don't care about it. So on what day is the temperature increasing the fastest? The 100th day of the year. And that makes sense, right? Because that's sort of right where spring is, and the temperature's increasing at the fastest rate before it starts to slow down as it gets to summer. That makes a lot of sense. So part A is 100. And then we want to know how many degrees per day is happening at 100. So we know what x is. It's 100 now. And we want to know what y prime is at 100. And if we look here, 100, oh, look, that's going to cancel out, right? So we got 36. Well, we've got 72 pi over 365 times the cosine of 0, which is 1, right? The cosine of 0 is 1, so 72 pi over 365. And that's, I don't know, that you do that in a calculator and you come out with, either you can leave it like that or you can just put it in the calculator. 72 pi divided by 365. You come up with like 0.6 something. So for part B, you want, it's increasing by 0.619. It keeps on going, but like here's the first 4 decimal places. And then degrees per day, that's your slope at that point, right? That's it. So yeah, that's what we have. We took a lot of time here. A lot of different types of problems, but again, once you practice these and once you get fluent at them, it's going to be really, really, really easy. Honestly, the more you do of these, the easier it gets. So take the time and practice. Take the time and practice this. All right.